Hello everyone, welcome to Cab O2. Today we are going to learn about enol and enol reactions. So let's get started. So we all know about a class of compounds in organic chemistry known as carbonyl compounds. So when we say carbonyl compounds, basically we talk about ketones and aldehydes. So we have seen many reactions of carbonyl compounds where they act as an electrophile. Electrophile as in we know that this C double bond O group of the carbonyl is polar. So if I draw the resonating structure, it looks something like this, negative, positive, and R dash. So we know that if there is a nucleophile, that nucleophile will be attacking on this carbon Y because as we can see in one of the resonating structure, it has positive charge. So carbonyl compounds behave as electrophile. But carbonyl compounds are the class of compounds which behaves both as electrophile as well as nucleophile. So electrophile, many reactions you must have seen. This reaction that I just saw, nucleophile attacking or carbonyl compound is an example of carbonyl compound acting as an electrophile. But these carbonyl compound can also act as a nucleophile. But the same class of compound, how can they act as both electrophile as well as nucleophile? That means they can be subjected to both nucleophilic as well as electrophilic reactions. So in this video, we are going to address that paradox and try to see how carbonyl compounds can behave both as an electrophile as well as nucleophile. So, for example, if you order a chemical compound from a chemical supplier, let's say you order cyclohexane, hexane 1,3 dione, or this is also called as beta dicarbonyl compound. Why is it called as beta carbonyl compound? This is alpha carbon, this is beta carbon. So with respect to this functional group, this C double bond, this second keto group is present at beta position. So therefore beta dicarbonyl. Why? Because there are two carbonyl groups present. Right. So if you order this chemical compound, obviously you will want to check whether this compound that the supplier has given you, whether it is pure or no. So we do what? We perform NMR analysis. You don't need to know much about the NMR, only that this is a technique this is an analytical technique used to determine the structure of a compound. So basically, if this NMR gives us only one type of structure, we will know that our compound is pure. Otherwise, if it gives any other structure, that means there is some impurity. So when we see the NMR spectrum, we basically find out that there is some impurity present. So the majority of the compound is what we expected, that is beta dicarbonyl compound or cyclohexene 1,3 dione in this case, but there is also some quantity, some amount of this also present. Okay, this is what we call as enol, and as the name clearly implies enol, that means there will be a double bond, there will be an alcohol functional group. So there is a double bond and there is an alcohol functional group. So enol. So basically, it's not like that the chemical supplier did not give you the pure compound. The thing is that this carbonyl compound has the tendency to interconvert to this enol form. So this chemical reaction reaction for carbonyl groups to convert into enol is called as enolization. Enolization. Okay, so what is the main difference if we see between carbonyl compound and the enol? The main difference is, first of all, the position of double bond. The C double bond, the double bond shifted its position to carbon-carbon double bond, and one of the hydrogens from this position shifted to oxygen. So that is the major difference. So a chemical reaction in which the intramolecular proton transfer is there. So if you see in this chemical reaction, what happened? This H from here got transferred to oxygen. Within the same molecule, it got transferred. So such kind of reactions are named as tautomerism. And these two compounds are said to be tautomers of each other. So what are tautomers? Chemical compounds which differ from each other only in terms of the position of a proton are called as tautomers. All right, so this is possible for all the carbonyl compounds. For example, if I take acetone, CH3, C double bond, CH3. So I will write H like this. So enol form of this is also possible. These electrons will shift here. Pi electrons will shift towards oxygen. This H plus will go to what? This oxygen, and you will have CH3, COH double bond and CH2. So this again you can see is enol form. En and alcohol group. So this particular reaction or tautomer is called as keto-enol tautomerism because keto form converting into enol form. So keto-enol tautomerism. In typical carbonyl compounds, the enol form is present in very trace quantity. For example, for this particular reaction, the equilibrium constant is 10 to the power minus 6, which means that the reaction almost favors backward direction. So almost all of it exists as keto form and not enol form. All right. So when will it be in significant enol form? That we are going to discuss very soon in this video. But for now, how do I confirm whether this tautomerism is happening or not? Because mostly this structure will exist as keto form only. So how do I confirm that? So the evidence can be provided very easily. So what you can do is you take acetone and then you do what? You keep it in heavy water, that is D2O, for some a considerable amount of time, like few hours or few days, and you will see that all the hydrogens present in acetone will be replaced by deuterium. So how is that possible? See, that is possible only through tautomerism. For example, CH3C double bond CH2H. So how will the tautomerism happen here? The hydrogen will give its electrons, carbon hydrogen electron bonds. The electrons of oxygen will shift up, okay, and you will have CH3, COH, double bond, CH2. Now, in order to go in the backward direction, what will it do? Oxygen will donate the electrons. These electrons will shift here. Now, because solvent is heavy water, that is D2O, this negative charge can abstract what? Deuterium from here. And when it does that, what will it form? It will form CH3, sorry, equilibrium sign, CH3C double bond OH positive, CH2D. These hydrogen will leave both of its electrons, so as to get rid of the positive charge, and you will have CH3, C double bond, CH2D. Now, similarly, again, one of the hydrogens can undergo keto-enol tautomerism, and like that, all the hydrogens can be converted to deuterium one by one. So, if I keep this acetone in heavy water for long enough, all the hydrogens will be replaced by deuterium. So, that tells me that yes, tautomerism does happen. All right. Now, like I said, that for typical carbonyl compounds, the very less quantity or very trace amount of enol is formed. Okay, so let's try and find out the reason for that. So you see, if we take the example of acetone, CH3C, this is the keto form, and in enol form, it will be CH3, COH double bond CH2. So you see, initially there was a C double bond, okay, and there was a carbon hydrogen bond. In the product, in the enol form, now we have new OH bond. One CH bond got broken and we have new OH bond. What else new do we have? We have a carbon-carbon bond, so carbon-carbon double bond is also present. So if we see energetically, carbon-carbon oxygen double bond and carbon hydrogen bond, this combination is slightly more energetically favorable as compared to oxygen, hydrogen, or carbon-carbon double bond. That is why we say that for typical carbonyl compounds, enol content is very, very less because the keto form is more stable and the reaction tends to move in the backward direction, that is towards the keto form. Alright, so I'm saying keto, but I hope you understand that other carbonyl compounds can also undergo similar tautomerism. For example, if I take aldehyde, okay, so what will happen in this case? There is one hydrogen present here. So this hydrogen can donate its electron. The pi electrons will shift up, and you will have C double bond OH and H. This is your enol form. Now, I hope you have noticed one thing that whenever I am representing keto enol, I show equilibrium sign. Okay, so these two are in equilibrium with each other. Don't use this sign because this sign is used for showing a resonating structure. These two keto or aldehyde or its enol form are not resonating structure. Okay, so you have to be very, very careful about the sign that you are using also. All right. Now, this is one of the questions that was asked in NEET. It says which of the given compounds can exhibit tautomerism. So you see, compounds containing alpha hydrogens can exhibit tautomerism. And what are alpha hydrogens? Hydrogens attached to alpha carbons are called as alpha hydrogens. Now the question is, what are alpha carbons? So basically, sp3 hybridized carbon atom directly attached to either sp2 or sp hybridized carbon are called as alpha carbon, and hydrogens attached to them are called as alpha hydrogen. So for example, here in this carbonyl, this carbon is sp2 hybridized. Everyone knows that. This carbon is what? sp3 hybridized, and it is directly connected. So this will be alpha carbon, and hydrogens attached will be called as alpha hydrogens. Okay. So because it has alpha hydrogen, yes, it will be showing ketoenol tautomerism. Let's check out this compound. This is sp2 hybridized carbon. This is the sp3 hybridized carbon directly connected. Are there any hydrogens present on it? Yes. So yes, this compound can also show. Now this is sp2 hybridized carbon. This is the sp3 hybridized directly connected. But does it have any hydrogen? No, because instead of hydrogen, two CH3 groups will be connected. So does it show tautomerism? Yes, it does. But you will say, sir, there are no alpha hydrogen. There is. Because see, this is also sp2 hybridized carbon. And to this one sp3 hybridized carbon is connected. And to this sp3 hybridized carbon, hydrogens are attached. So these hydrogens are also called as alpha hydrogens. Okay, and it can show. So if you want me to show one of the tautomers, double bond, CH3, CH3, and double bond. So how will it show tautomerism? The alpha hydrogens. So these two electrons will shift here, these pi electrons will shift here, these pi electrons will shift here, and the enol form formed will be OH. Alright, fine. Now you see, we have seen that enol forms are generally less stable as compared to their keto form. Why? Because it is energetically more favorable. The carbonyl compound is energetically more favorable because of the C double bond and CH bond. But in some cases, enol form is actually quite stable and is present in significant quantity. To give you a very common example that all of you have definitely heard of is phenol. So if you look at the name phenol, so phenol is basically what? An enol. So let's look at it. What is the structure of phenol? This is the structure of phenol. So here we see that there is double bond also, and there is OH group also present. Now this phenol is enol of what kind of carbonyl compound? So it is very easy if you want to draw that structure. So we have our phenol with you. Let me start again to show you the structure of its keto form OH double bond double bond. So these electrons will shift here, these electrons will shift here, and you will have double bond O. This is your keto form. And what is the enol form? This compound we know is phenol. So we know already that phenol exists as this structure rather than this structure. Why? Because see, in this case, this ring is aromatic, which makes this compound very, very stable. So there are instances where enol form is stable and occurs in significant amount, sorry. All right. Now see, there are other examples also. C double bond O, double bond O. These types of compounds are called as 1,3 dicarbonyl compounds because see, if I consider this as first position with respect to that first carbonyl compound, this will be third. So generally in 1,3 dicarbonyl compounds, the enol formed is quite stable. Let me draw those enol forms and show you. So in this case, what is going to happen? Double bond O and double bond O. There are two hydrogens present on alpha position. So what will this do? This hydrogen will donate its electron. These pi electrons will shift up, and the enol form for this compound is going to be OH double bond. Now this enol form is also quite stable for two reasons. Why? First of all, you can see the lone pairs double bond and this double bond are in conjugation, so there is extended conjugation. That is one stabilizing factor. And the second stabilizing factor, if you look carefully, is hydrogen bonding. To show you that hydrogen bonding clearly, you can see the hydrogen attached to this oxygen can show hydrogen bonding with this oxygen, forming how many membered cyclic transition state? 1, 2, 3, 4, 5, and 6. So H bonding is also the reason why in this case there is significant amount of enol content. What are those reasons? Extended conjugation as well as hydrogen bonding. Now this mechanism of enol formation, basically see, in neutral medium also keto form can be converted to enol form. But these reactions are typically very slow and it will take hours or even days for them to have any significant amount of enol form. So in order to speed up these reactions, what we can do is we can use catalysts, and those catalysts can be either acids or bases. So acid, base, catalyzed tautomerism. So the mechanism is actually very, very easy. So let's talk about acid catalyst tautomerism first. So we have our carbonyl compound. Okay, in acidic medium, what will we have? We will have H plus. So the lone pairs of oxygen are going to do what? They are going to take up H plus. So it will form OH positive. There are alpha hydrogens present here. These two electrons will shift here. These two electrons will go there. Who will assist the removal of hydrogen here? Water that is present as solvent. So what will happen in the end? COH double bond and hydronium ion. I hope everyone knows that hydronium ion is basically equivalent to H plus. So why is that information important? Because you saw in the beginning we took H plus and at the end we got our H plus back, which tells us what? That H plus was used as a catalyst because it did not get consumed during the reaction. So this is how the mechanism happens in acidic medium. Now, if we talk about the same thing in basic medium, when I say basic medium, what does that mean? That there are hydrogens, OH minus present, right? So that OH minus will do what? Will abstract this alpha hydrogen and a conjugate base will be formed. This negative charge will shift here, this will shift here, and you will have, so now see the arrow that I'm showing is what? Of a resonating structure because O minus double bond this and this are resonating structure. All right. So water that was formed in first step, Negative charge will take up H plus, and you will have your enol form. So this reaction can happen both in acidic as well as basic medium. So see, this reaction can happen in neutral medium also, but in order to speed up the reaction, we are using acid as well as base as a catalyst. As you can see in first reaction also, we got back our H plus. In second reaction also, if you see after taking H plus from water here, you will get back your OH minus. So both first as well as second reaction are catalyzed, first one with acid, second one with base. So let's see some reactions based on this enol form. So one of the reactions that you must have seen is halogenation of carbonyl compounds, right? So halogenation of carbonyl compound basically is very easy to understand once you understand the concept of enol form. So for example, if I have a acetone with me and if I want to react it with Br2 in the presence of acidic medium. So let's say I took acetic acid. So the product will be that bromine will be connected to this carbonyl compound. Now let's see the mechanism, how this is going to happen. So if we talk about the mechanism, see it is going to be very, very easy. In acidic medium, we will have H plus, carbonyl compound is there. So what will happen? Oxygen is going to donate its electron to H plus, right? So you will have OH positive. Now there are alpha hydrogens present. If I show you the alpha hydrogen, this is what it looks like. Now what will happen? These two electrons, hydrogen will donate. These electrons will shift up. Why? So that the oxygen gets rid of this positive charge, and you will have your enol form OH double bond. Now when these electrons come back down, because enol form is slightly less stable than keto form, these electrons will come towards carbon. The bromine molecule that is present will be acting as an electrophile. We know that halogen molecules are electrophile. Why? Because there is instantaneous dipole present. So that negative charge is going to attack on bromine. This bromine is going to leave. And the product form will be C double bond OH positive and Br. This hydrogen will leave both of its electron to oxygen, and halogenation of carbonyl compound has happened. So that is how the halogenation of carbonyl compound proceeds. Similarly, there is one more reaction that you must have learned, that is haloform reaction. Okay, so haloform reaction also becomes very, very easy when we go through enol mechanism. So to give you the general reaction, what happens if you react a carbonyl compound with NaOH in the presence of halogen molecule X2, where X can be, it can be chlorine, bromine, or iodine. So it will give you sodium carboxylate ion plus CHX3. This CHX3 is called as what? Haloform, and that is why the name haloform reaction. So if it is CHCl3, it is called as chloroform. You already know that. If it is CHBr3, it is called as bromoform. And if it is CHI3, it is called as iodoform. Now let's try and see the mechanism here. So mechanism is again very simple if you understand the enol form. So we know that carbonyl compounds in the presence of basic medium can undergo keto-enol tautomerism. So there is this base present OH minus. This OH minus is going to do what? Abstract this hydrogen. You will have your conjugate base minus. You will have the negative charge in conjugation, O minus and double bond. Now what will happen? This negative charge will come back down. These electrons will shift here. Bromine is what? Your electrophile. Why? Because there is an instantaneous dipole. Again, same thing. Or rather than bromine, let me write down XX to make it general. X can be any halogen, chlorine, bromine, or iodine. This is going to attack on X. This is going to leave. You are going to have C double bond and X. Now the thing is, here the reaction won't stop here. Why? Because see, once the halogen has happened, Halogenation has happened. There are two more hydrogens left. Now base will be tempted to abstract these alpha hydrogens also. Why? Because this hydrogen is now even more acidic. Why? Because of the presence of this halogen group. So see, if this OH minus abstracts this alpha hydrogen, you will have X minus, this will be your conjugate base. And this conjugate base is stable. Why? Because of the minus I effect of this halogen group. Obviously, conjugation is also there, but there is minus extra minus I effect, stabilizing effect of this X group also. So again, now what will happen? This will convert into enol form, that is O minus double bond Br. These electrons will shift down, these electrons will come here. Br2 molecule, or okay, I'm using Br somewhere X somewhere, sorry. Let's make it X again. So XX molecule will be there, del positive, del negative. This negative charge is going to attack on X. This is going to go away. And you will have C double bond X and X. Now I hope you see that this one more hydrogen left is even more acidic. Why? Because now there are two X groups which will apply minus I effect and therefore making it very, very acidic. So I'm not going to write the mechanism again, but you understand that all three hydrogens will be replaced by X. Now, when there is no more hydrogen and there is base present, what will this base do? This base is going to attack on this carbon, del positive, electrons are going to go up, they're going to come down, and they are going to expel this CH3. Why? Because this CH3 now is a good leaving group. As you will see, it will form OH plus CX3 minus. Why is this CX3 minus stable? Because of presence of three halogens which are minus I effect showing groups. And because this is an acid and this is a base, acid-base reaction will happen. You will have C double bond O minus plus CHX3. This is your halogen. And counter ion is sodium. So that is how you get your product. Now, this reaction is used as an identification test for carbonyl compounds having C double bond O CH3 types of groups. Okay, so if carbonyl compounds having C double bond O CH3 types of groups are reacted with NaOH and I2, so the product formed will be what? CHI3, that is iodoform. And this iodoform is what? Yellow in color. So we can test for any carbonyl group which contains C double bond O CH3 group to this haloform reaction. Now sometimes in exam they will try and confuse you. They won't directly give you compounds containing C double bond CH3. They will give you alcohol. So for example, they will ask you, will this compound give iodoform test? So the answer will be yes, it will. But you will say, sir, there is no C double bond CH3 group. See, NaOH I2, in the presence of NaOH and I2, this 1 degree alcohol will be oxidized to ketone, that is CH3. So not ketone, aldehyde, C double bond H. And now it is a carbonyl group containing CH3 C double bond O. So this combination will act as an oxidizing agent and will oxidize this alcohol into aldehyde. So for example, if someone asks, will this compound show iodoform test? So the answer is yes, it will. So all the compounds containing C double bond or CH3 group will show this iodoform test. That means methyl ketones will definitely show, acetaldehyde will show, all the alcohols which can be oxidized to either methyl ketone or acetaldehyde will also give iodoform test. So I hope you understood enol and reactions related to enol. That's it for this time. See you soon.